I think we can talk about
So
it. I think we
the
can talk about it.
Navier-Stokes equations,
Oh
right,
my.
are a set
Absolutely.
of equations, and they pertain to the motion of fluids.
Mhm.
Now let's get really elementary in here.
Okay.
A fluid is anything that flows, aka a gas or a liquid,
Some solids
right?
do. Take that. Like glaciers, for example, like they have motions of flowing. Like if you see like a glacier
Mm-hmm.
falling, it will follow a path. And a very common description of fluids is that it fits its container, right? Like water will kind of fit the level of glass kind of thing, and a gas will fill up its entire container. So the idea is that a solid, much like a glacier, like I guess a glacier, you can think of it as, at the end of the day, it is liquid, but a big part of it, a glacier falling down, you don't really expect it to conform to certain levels in the container, but it does, right? So there are even some certain scenarios. Yeah, continue.
I mean, I think that has more to do with like friction than it being a fluid, right? Because if
Okay, it's
it's
not a
just like
fluid. What I meant to
it's
say, it flows. It's not a fluid.
okay,
It's not, solid is not, solids are not,
okay,
I don't, yeah, solids are not
I
fluids.
respect
No.
that.
Yeah, yeah.
I respect that.
Okay.
And so I just want to say that within fluid dynamics, what you and I have seen so far is just like the flux of a fluid.
Mm-hmm.
And also Bernoulli's
Bernoulli's
law, is that what it's
Bernoulli's
called?
principle.
Oh, principle.
Mm-hmm.
Right. And I think that's it. Like that's all
Yeah.
we've seen, right?
We haven't really personally done a lot, because the thing with fluids is that it gets extremely complicated to the point where there are things that even these equations can't predict. And I kind of skipping the horse, jumping up here, but an important part about fluids, or especially with air, and this also works with liquids, but you can apparently very obviously tell with air, is turbulence, right? Turbulence is one effect that cannot be predicted. Or at least today, at least till what we know today, it cannot be predicted. And obviously, right, because if you think about it, the entire idea of turbulence is these random particles that are hitting each other and going off in weird ways. Let me give you an example, right? At the corner, at the very edge of a wing, like obviously you probably won't see this from an airplane because you're in the airplane, but if you, like, I don't know, any airplane, at the very edge, they have that, what's that thing called? They have that thing, like, they have that thing to kind of cut through the wind.
I don't know what the name is.
And you'll be able to see at the very edge, as it's traveling at, 700 kilometers an hour, you'll see at the very edge there's a vortex that's forming. And the reason behind that is because all the air that is coming on top and below is all hitting at that one part, at that one point. And at that point, there is no equation, no model solution that can predict what happens at that point, because of turbulence. Turbulence is the entire idea of random motion. And this is actually a big problem with the Navier-Stokes equations. So, I mean, like I guess we're talking about it now, but like turbulence, especially with water too, like if water waves crash together, where will each and every particle go? Well, we don't know. Even if we model each and every particle, there are random motions that sometimes just simply can't be taken into consideration, right? Because we just don't have all that knowledge. So a lot of this, again, Navier-Stokes equation helps, but it doesn't tackle every possible real life scenario, that being turbulence.
Mm-hmm.
Right.
And for example, one way in which the Navier-Stokes equations do fail is that, let's say you have a corner, right? You have water flowing in one direction, and then it turns on a 90-degree angle. And so you can tell that on the outside of that turn, the water particles are going to be, going one way and then turning.
Yeah.
Right? But the closer you get to the inside corner, the faster you have to travel, right? Because you have to go from one direction to another direction. But it's kind of like circular motion, right? So as you're turning, you have a radius of rotation, And obviously the closer you are to that radius, but you have the same velocity because all the particles are coming along the trajectory in the straight line at the same velocity. But as they start rotating, the ones on the outside have a larger radius for their rotation, so they will be moving slower than the ones closer to the corner. But here's the thing: the particles of water, or the molecules of water that are turning directly on that corner will actually have infinite velocity.
Predicted by the Navier-Stokes equation.
Yeah. Predicted by the Navier-Stokes equation. Of course, we already know that that's not possible.
Impossible.
Right? we already know that infinite velocity is not possible. Right? You know, every time you form a corner with water flowing on it, you get a black hole forming. You know, I think we would know about that by now. The point is that you can have computer solutions, right? Or like computer approximations to these problems. And it just goes by, I think it's like iterating the simulation or whatever. They can get like an approximate velocity, but according to the math, it should just blow up to infinity and you would get no solution. So that's what has to be solved, you know? Why does this happen? And is there maybe a correction, hypothetical correction that can be brought to actually account for these discrepancies, I guess?
Because I guess there are two ways to answer this question. Either, no, it does not blow up to infinity because of this, and this is what happens instead. Or, yes, it does blow up to infinity, and this equation simply does not work in this case. So those are, I guess, the two options for solving it. And obviously you need a very, very, good description of where and how you came to that inference. But basically, that's it. So the Navier-Stokes equations, again, are equations. But the problem itself is not called the Navier-Stokes equations. The problem itself is called the Navier-Stokes existence and smoothness. Now, you might be wondering, that's a pretty interesting name. What do they really mean? So, the idea behind existence and smoothness is existence. There must exist a unique solution for any inputted value. So, let's say I have these two equations. So, they're actually a list of two equations. The first equation is basically relating how mass is conserved. It kind of relates the velocity of the particle and everything. I don't want to get too deep into the actual equations themselves, but just talking about them. The first equation kind of states how mass is conserved, and the second equation states how momentum is conserved by using Newton's second law. Right? So you might be wondering, well, that obviously is correct, right? Like it makes sense. But again, as Parker stated, like there's some moments, there's some locations where this equation simply does not work. So anyways, existence, there must exist a unique solution to a set of inputted points. So if I input a certain velocity, a certain trajectory, going in a certain way, I should be able to get, certain outputs. And if I change it a little bit, I should not be getting the same output. And the output should be unique to each input. So that's the first argument. It must be a unique it must be a unique solution if we were to find a solution to this problem. And the second one is smoothness. Now, smoothness is very interesting because if, let's say, I have a bunch of parameters, right? I have a bunch of velocities that are going in a certain direction, and I get some certain output. Smoothness basically states if I change one parameter, just infinitesimally, if I just change it a little bit, it should change the output just by a little bit. Problem is, a lot of times this doesn't happen, right? By changing the input parameter just a little bit, it sometimes blows up the output parameter to proportions that don't make any sense. And that right there is another problem, right? So I guess the idea to, again, solve the Navier-Stokes equations would be to show that there is a unique solution for every single possible input. And that unique solution, whatever is outputted, will not change too much if the input is also changed. So it's also smooth. And that's another important part of the equation.